In this video, we'll be looking at the concept of error correcting codes. Now, the ingenious thing about error correcting codes is they don't just detect errors like our CRCs and parity and LRCs and those checksums do, but in some cases they can actually repair errors, fix errors, without requiring us to resend the data. Because that's what would happen when we detect something with a traditional checksum. We detect an error and we're like, please resubmit, or please resend that data to me. And in this case, what we can do is we can embed some redundant data in the data we're actually sending, and we can correct a limited number of errors. So error correcting codes have been around for over 70 years. So Richard Hamming, a mathematician from the US, invented these a long time ago. And we often refer to them as a form of forward error correction. Now, there is some significant pros around using error correcting codes. One of them is latency. For error messages, we don't need to wait until that message is resent again. For example, we receive a message, it's got an error, and you send a message back saying, please resend, and it gets sent again. Some circumstances, for example, when we're using low power systems or LoRaWAN systems and things like that, we might want to avoid that sort of thing because we're trying to be off or asleep most of the time. Or if we're sending data a very long way, for example, the latency, the turnaround time to get from Uranus, the planet, down to Earth is 5 hours. And so that's a long time to actually wait for that message to be resent. One of the other pros is we don't need data going necessarily back in the other direction. So it can be a one-way form of communication. We don't need to have any functionality to request the data be sent again because it's been sent. Having said that, one of the cons is obviously the data overhead. I mentioned we're integrating some redundancy in here in our forward channel where we're sending our data out. And because we're integrating some redundancy in there, we're sending more data. But the pro is that even if there is an error, you might be able to correct that error. And that's a pretty significant pro. Well, first off, let's look at a really inefficient version of an error correcting code. Now, this inefficient version of an error correcting code, basically what we do, we use TMR, triple modular redundancy, by time. So we send the same bit 3 times and vote. So this is massive overhead. For every bit we're sending, or every data bit we're sending it 3 times. So we're sending 3 times more information than we necessarily need to send. Having said that though, we could still have some errors. For example, if it's all stuck high or all stuck low, we're in trouble. If we have a 1-bit error, we can detect that error and correct it because if it's, for example, 100, well, we know it's going to be 0 because the other 2 bits are 0, just with TMR. But if there's a 2-bit error, it actually falsely corrects it and thinks it's actually something else. Now, there's some ways that we can get around this if we've got, we might have a string of bits that are all pulled high or all pulled low. One thing you can do is called interleaving the bits, where you don't just send them one after another, where you might get all 3 pulled high or all 3 pulled low, but you mix them up among other data and you interleave that data. So if a whole bunch get pulled high, well, that whole bunch are going to be actually possibly different bits, not just the same bit that's been sent 3 times. And so hopefully when the other ones are sent, sometimes in the future, the other 2 times it will correct for that. Now, I mentioned that sending it 3 times wasn't very inefficient. In contrast, Hamming code is a much more efficient way to do things. And there's a few different varieties of Hamming codes. So Hamming codes can detect 2-bit errors. Before we could only detect a 1-bit error, and it can correct 1-bit errors. So as I said, 1950, these were invented by Richard Hamming, and they're used in memory, for example, ECC, error correcting code memory, that we may have on our computers. Basically what we have here is not just one, but multiple parity bits for each block of data. And what we do is we map those parity bits to overlapping bits in our data. And what we do is we use those parity bits to work out which bit in our data, or in fact the parity bit, is in error. And once we've worked out which one is in error, we can flip it and make it not in error anymore. Now, there's a bunch of different variants of Hamming codes. For example, Hamming 7.4 uses 3 parity bits and 4 data bits, so 7 bits in total. Now, that's not super efficient. There's a fair bit of data that we're still sending out, fair bit of overhead that we're still sending out, but it's a lot more than sending the same thing, the whole same thing 3 times, and it gives you extra functionality than that does. Hamming 1511 has 4 parity bits for 11 bits of data, so 15 bits total. So that one's a fair bit more efficient, and there's a number of other versions of hamming around. Now we'll have a bit of a look at how we actually map our parity bits, or how we actually store them. And so the way we do it, we essentially number our bits in binary. So starting at bit 1, or which will be 0, 0, 0, 1, or however many zeros we're using there. And then bit 2, bit 3, and bit 4, and so on and so forth, however many we're using. And what we want to say is that parity bit 1 will cover all the bits where our least significant bit is a 1. So we've got a 1 there, we've got a 1 there, we've got a 1 there. It's going to cover, for example, 1, 3, 5, and 7. And the parity bit will actually be the first one of those, that particular one there. The parity bit we store whenever all the other bits are a 0, and we've just got a 1. So this will be parity bit 1. This one here will be parity bit 2, which is when all the other bits are a 0 except for the second least significant bit, which is what we store in there. And so that covers whenever our second least significant bit, for example those ones, in cases 2 and 3, and if we draw one more, in case 6, where our second least significant bit is a 1. And then parity bit 3, our third one, which is what we store here in bit 4, that's going to cover whenever we've got our third least significant bit as a 1. And we store P3 in the first one of those. There it is in the table, so we see it again, and we've just colorized it as well. So whenever our least significant bit is a 1, we'll have a parity bit that covers it. Whenever our second most least significant bit is a 1 in purple, we've got a parity bit that covers it, and so on, depending on how many parity bits we've got, and depending on what hamming code we actually use.